Okay, good morning, everyone. Thank you for joining in. I think this is our first truly hybrid event where we have in-person, first DLS after COVID, as well as people joining online. And there is a viewing room in this building as well upstairs where they are also located. So I'd like to start acknowledging that the Waterloo Institute for Nanotechnology at the University of Waterloo sits in the traditional territory of the neutral, Anishinaabe, and Haudenosaunee people. The University of Waterloo main campus is situated on the Haldimand Tract, the land granted to the Six Nations that includes the 6 miles on each side of the Grand River. Since some of you are already online, I would like to invite each of you to reflect on where your feet are planted and explore who shares the land base, the colonial history, and what transformative acts can be achieved over the coming decades towards reconciliation and justice. It is such an immense pleasure to have Professor Yury Gogotsi with us, giving this WIN Distinguished Lecture Series seminar. Professor Gogotsi is a Distinguished University Professor and Charles T. and Ruth M. Bach Professor of Material Science and Engineering at Drexel University. He also serves as the Director of A.J. Drexel Nanomaterials Institute. His key contribution to material science includes the discovery of MXenes and development of family of carbide-based carbon with tunable structures and porosity. He has published over 800 journal papers and the most highly cited researcher in the world. He is the fellow of almost all academies that you can think about in the world. So we are so fortunate, and it is really his real, availability, and he's so generous in his time that he's able to spend this today, the entire day with us at the Waterloo Institute of Nanotechnology at the University of Waterloo. So Yury, the floor is yours, and we are looking forward to this.
Thank you very much for this kind introduction, and thank you very much for inviting me to speak. And I hope you can hear and understand me better without me wearing mask here. So first, I'm delighted to be here because this is my very first visit to University of Waterloo. But I've heard a lot about the university, about WIN Center. I'm familiar with the work of a number of colleagues, including Professor IPNU, who is here, including Linda Nazar, who I meet at pretty much almost every conference on energy storage and electrochemistry I go to. Last time at the MRS meeting about 2 or 3 weeks ago. Things here. So I'm really happy to be here. And what I'm going to do today, to introduce you this family of 2-dimensional materials, which we called MXenes, which we discovered about a decade ago with my students, colleague at Drexel. So those are carbides and nitrides of transition metals with structures shown in this picture. And they come in a variety of flavors, colors, plasmonic colors, which actually enable a huge number of applications. They also have many useful properties. So my goal is today to introduce you to this family of materials. I won't be able to delve into every single application or property. I hope that after listening my talk today, you may be interested in exploring them, whatever your area of application is, from structural composites to photovoltaics, to energy storage, to optoelectronics, cancer treatment, or many, many others here. Because it all starts with material discovery, and that's what we do here. But just before I start my lecture, a couple of words about myself. I was born and raised in Ukraine. I got all my degrees from Ukraine. And actually, well, I already see another typo here. It should be not 2019, it's updated date. It was actually 1995. Dr. Hnore Kauzar gets here. But this is the front of the first building of Kiev Polytechnic. Dmitry Mendeleev was on the board founding it, creating the technological university, just like similar to University of Waterloo in Kiev. And I'm here with my brother and my father, who are all graduate of Kiev Polytechnic. My brother is also a scientist, and my father is a scientist in Ukrainian Academy of Sciences here. And I traveled, I started my work actually working on carbides and nitrides. but on a bulk scale. At the time of structural ceramic interest, developing ceramics for high temperature application for engines. But when I did my postdoc in Japan at Tokyo Institute of Technology, I started to work on carbon nanomaterials. We discovered a way to make hydrothermal nanoporous carbon from carbides here. And pretty much I dedicated the last 30 years of my life to nanomaterials, nanotechnology. First 20 years were carbon nanomaterials, but currently I have about 40 people in my research team working on this two-dimensional carbides and nitrides, often combining them with carbon with other materials, which I'm going to discuss today. So currently I'm at Drexel University in Philadelphia in Pennsylvania. For people who are not familiar with the US East Coast between Washington, DC and New York. And Drexel University was founded actually at about the same time with Kiev Polytechnic. And you can see maybe there is some similarities construction style. And also it was founded, you probably won't be able to read it here, but it's written here, Drexel Institute. It was created as Institute of Technology with the goal actually to educate engineers and complement University of Pennsylvania, which is like a first university in the US founded by Benjamin Franklin here. So you see like my education and career are closely connected to technological university, and you can go to our website to learn more about what we do here. And this is the building which hosts our Nanomaterials Institute, and my labs occupy actually the entire third floor of this building. And this building was designed by IMP, the same architect who designed pyramids of Louvre. You may recall this glassy pyramidal structures here. So we have quite a modern lab here. So now about what we do. By education, I'm metallurgist, physical chemist, material scientist. And my group works primarily on nanomaterials, developing materials. And I'm a strong believer in the role of materials in society. Well, you know, like from Stone Age to Bronze, Iron Age, and currently we live in the Silicon Age because our computer is based in silicon. Progress of humanity was really defined by materials use, because material enable us to do things, pretty much create everything. And I also believe that we are, jumped too far ahead here, that we're moving to the age where really nanomaterials and nanomaterials which are biomimetic, multifunctional, which are hybrids of very different materials, will allow us to really build first materials atom by atom, and then combine these materials to build devices, to build metamaterials, to build structure, which have properties that no single material can offer here. And this is where I believe will be the future that will take us to area of quantum technologies, which will take us to area of real Internet of Things, wearable Internet here. And we're trying to provide building blocks basically for this future, for future technologies. And we work on two-dimensional materials. And clearly everyone is familiar with graphene. Kostya Novoselov, Andrew Gaim at Manchester discovered them in 2004, or really they didn't discover it. They separated single layer of graphene and showed its interesting physical properties, new physics there here. But this discovery really led the world to first recall, oh, we have already other 2D materials. Actually, moly disulfide was separated as single layers even before graphene. But the most commonly used nanomaterial is clay. Clay are two-dimensional silicate particles, which actually you'll find in the bumper of every car in all these polymer matrix composite materials. So tonnage-wise, this is the most used nanomaterial in the world, for sure. But there are many others, and they have interesting properties. But what is also amazing, in addition to non-nanomaterial, like TMDs, like oxides, layered double hydroxides, people started to create materials which don't have layered van der Waals bonded precursors, like silicon, germanium, which have cubic diamond structure, it appears possible to make them in two-dimensional state here. And in 2011, we showed that carbides and nitrides of transition metals that also exist only in a bulk like a cubic sodium chloride structure can also be made in a two-dimensional state. We call these materials MXenes, where M stands for a transition metals, those atoms on the surface, and X stands for carbon and nitrogen, atoms connecting transition metal, for example, titanium or moly, silicon, other things here. And in is the suffix people traditionally add now to two-dimensional materials, even if it came to graphene from organic chemistry, and there is nothing organic in those materials in here. So what is important? Why 2D materials really are enabled? Because you can use them as bricks on Lego stone to create dense structures here. You cannot connect zero-dimensional like quantum dots or nanodiamond particles the same way. They cannot make a cohesive, robust structure. From single-wall nanotubes or nanowires, you can build something like a mats. But again, you don't build a building this way, for example. Here, you don't build an electronic device this way. 2D materials allow you in plane or in 3 dimensions in any way really build. That's why 2D materials appearance really enables nanotechnology to move from some separate exotic application or being additive to something to really building new generation of materials and devices. But if you look at all the 2D materials known, there have been many of them dielectric, oxides, hydroxides, semiconducting, TMDs, for example, here. But graphene, which is always praised for its high conductivity, in fact, is zero band gap semiconductors. It doesn't have carriers. You have to dope it or create defects to create carriers in graphene. MXenes that we added are true metals, many of them it is, majority of them. So they added two-dimensional metals to the family of 2D materials. And this is why they have this important role. We not only play the opening game in science here, to a certain extent, we play the closing game, adding a family of 2D materials which was missing. Materials with metallic properties. Now we have dielectric metal semiconductors. We can build pretty much any kinds of devices. But they are very unusual metals. They are also terminated by typically oxygen OH, or as you showed you later, you can have halogens, chalcogens here. So they're metals that actually can have on the surface transition metal oxide-like, hydroxide-like, chalcogen-like termination that can change the oxidation state without killing its metallic conductivity. You know, in graphene, you make a graphene oxide, conductivity drops down by 7 orders of magnitude. In MXene, it won't change. Consider it to be like in an ocean, because when you have a structure, it can be a thicker structure like that. When there is a storm on the surface, electrons here in the middle don't know about it. They still can be conducted. So you have metals which have hydrophilic surface with ability to change the oxidation state. You can use it in energy storage, as I will show later today. Things here. You can dissolve them in water, like a water-soluble metal, or if you want a conducting clay. And those properties by themselves are very unique. No combination exists, to the best of my knowledge, is available in any other family of materials. There is something else. The metals, they have high density of state at the Fermi level, high concentration of carriers. By changing these atoms on the surface, especially when you go to so-known 2-1 structure with 2 layers of transition metal, pulling electron density, you can open band gap, or you can change basically the Fermi level. So what does it mean? You have metals, but are tunable. Why is all electronics based on semiconductors? Because in semiconductor, you can change the band gap by doping, by injection charge. Metals are boring. You take a piece of gold or copper, and it always remains the same. Here you have metal, but metal which is tunable electronically, or chemically, or electrochemically, which is again very unique properties, allowing us to do things that cannot be done with other materials. And of course, they come in a variety of flavors, as I mentioned to you. We can have different number of transition metal, carbon, nitrogen. We have different layers. And also, we can have different surface termination. And Michael Nagib, PhD student who worked with myself and Michel Barzum, who was the first discoverer of this material, during his PhD study, reported like a dozen of different new MXene compositions here. Moreover, you can notice we can not only have different transition metal, carbon, nitrogen, but can make solid solution on X side, carbon nitride. We can make solid solution on M side. So we have huge number of materials. Last year, Advanced Materials was the first MXene discovery. Titanium 32 was published here, had a virtual issue dedicated to MXene. And you can see those a picture from this, how quickly now research started. But actually, in the first year after discovery, there was very little going on because it was on the wave of graphene Nobel Prize, a lot of other 2D materials explored. Initially, people thought, of course, why do we need more of 2D materials? There are already so many discovered here. And only when these new properties were really realized and appreciated, and in pretty much almost every single application where people tried graphene, MXenes outperform graphene. This is where this interest and very fast growth started here. And you can see every year, more and more MXenes were added to the family, and there is still plenty of room to discover. So how do we make them? Where does this name actually came from? There is a large family of layered ceramic materials, which is called MX phases. You can look at them at layers of carbides or nitride separated by monatomic layers of another element from this group, A element from blue one. So we have these transition metals possible, carbon, nitrogen, and these elements. What we did following the work we did before on carbon materials, selective etch, we just etched, removed these elements. In fact, you can use also other layered carbides, nitrides, which are plentiful in other families, not related to MX phases. But initially, we etched away A. What is left was M and X. This is where MXenes came from here. What is important? Those materials have strong bonds between the layers, metallic covalent ionic bonds. You cannot share them like you would share graphene, for example, and produce graphite, and produce graphene or molybdensulfide. You have to chemically separate them. But after you etch them, there is this surface termination coming. We mark them by letter T, often like terminations here. And now you have particles which look largely like thermally expanded graphite or vermiculite clay, for example. We have seen SEM pictures of those. And now there are weak van der Waals bonds between the layers. You can delaminate them by intercalation, other methods here, and get single layer particles from those materials. Now, what do we have? We have these 4 structures possible so far, from M2X to M5X4. We have these transition metals, and you can add, of course, all rare earth metal to those. You can have carbon and nitrogen. You have at least 10 surface termination, oxygen, chalcogens, or halogens, hydroxyl groups, amino groups on the surface here. And you can also intercalate between the layers variety of other elements. So pretty much we can almost like have access to designing using the entire periodic table of majority of elements. Some that are not there probably still have not been put there. So what do we have at the moment? We have a huge variety of 2-dimensional materials that we can actually design based on required properties. So we can have M2X, M3X2, M4X3, M5X4 structure. It means that every layer, every sheet, 2-dimensional sheets will have exactly the same thickness. And actually going to higher, larger thickness is important. Graphene, molybdensulfide, they are flimsy, they are very thin. Those materials being nanometer thick, much, much stiffer because the bending modulus inversely proportional thickness power 4. So it makes a huge difference, for example, in developing resonators, other structures, building out these materials here. But we can also push nanoscale design further. We can make materials with like atomic sandwiches, like one layer on the surface will be, say, moly or chromium, another layer in the middle will be titanium, or 2 layers of titanium in the middle. And we can make materials with alternating atomic columns of different atoms. And if we remove one of them, for example, like tungsten, yttrium carbide, you etch away yttrium, you're left with tungsten, and you're left with layers of like atomic columns of vacancies on the surface. So we basically really do atomistic design in two-dimensional space. And this is definitely not the limit, because there is theoretical prediction of more complex and diverse structures here. And let's just do math. You have like a 12 transition elements, carbon, nitrogen, and 4 different structures. You already end up with at least 100 of stoichiometric compositions here, not counting this type of 26 have been predicted theoretically out of plane ordered, and another probably 20, 30 in plane ordered structures here. Now multiply by 10 surface termination already available, you end up at least with 1,000 of stoichiometric compositions within MXene structure. But we have all the solid solution, and even high entropy multi-element MXenes were reported last year. So you basically have virtually an infinite number of possibilities. We just need to learn how to design them, how to synthesize them, and how to use them here. And we can build a new world with this material things here. But only about 50 have been experimentally produced so far, because someone needs to go to the lab, make a max precursor, make a MXene, characterize it, and so on. So there is plenty of room left for discovery for younger people in this room in that field. Now, we have this huge family of materials. But you know that there are probably already about 200 at least of 2D materials have been experimentally reported, more than 1,000 predicted, or 2,000, I believe, lately, if count simple MXenes, have been predicted theoretically. Still, what is important? Except clay, graphene, boron nitride, moly disulfide, tungsten disulfide, and a couple of others. All of them are produced in milligram quantities. Many of them are produced by CVD, PVD, like a monolayer, moreover, unstable monolayer, gallium nitride with a big fanfare was reported by Penn State, or borafine, which attracts a lot of attention, but still no one can really take it off like a single high quality flake of silver substrate and even measure its properties properly. We, from the very beginning, were making this material in large quantities, because we take ceramic powder, we dump it into a reactor. Actually, this was designed by a Ukrainian small company for us. Here, get MXene, delaminate it, wash it, and produce the material. Here is my postdoc, John Jung, holding 1 kilogram of MXene. Sorry, pushing wrong buttons again. 1 kilogram of 2D material. And within next 4, it was all done within 24 hours, produced within the next 4 days. My student delaminated completely in single flake solutions, and we got 8 20-liter containers of colloidal solution in single layer flakes, because it's hydrophilic. It has OH groups on the surface. So if you put it in water, it dissolves, as you can see in this middle image. If you make more concentrated solution, we use it, for example, for inkjet printing. Beautiful paper today in Nature Communications coming from Switzerland and Chinese collaborators on printing all kinds of devices using MXene ink. Moreover, just water, nothing else needed to it. Or you can make a 6 slurry that you can use to draw fiber. It is liquid crystalline, or for example, printing by other techniques, doctor blading, or screen printing, colloidal solution. So basically, you can get any kind of dispersion with viscosity needed here. And it's all possible because high negative surface charge, zeta potential below minus 30 millivolt, allows us to create stable colloidal solution in water without adding surfactant or anything. And this is again a big difference compared, for example, to graphene, when you can work with graphene oxide in water, but you want to back it to conductive form that is usually used in most of application, you need to reduce this, or you have to use surfactants or additives here. So we go all the way from ceramic powder to this type of a clay, MXene clay, we call it, because it's really like a clay containing some water between the layers, two-dimensional OH-terminated, oxygen-terminated flakes, to colloidal solution. You can see here a liter of bottle with typically 10-20 microns. But you see also they have different colors. Unlike graphene, I'm comparing to graphene because it's kind of the most common materials most people know. It's not that all shades of gray, those are colorful. But moreover, remember, those are plasmonic colors. I will come back to it later in my talk here. Now, if you have colloidal solution of two-dimensional flakes in water, you can process it the same way as people have been processing other colloidal solutions. There is nothing you need. It can be inkjet printing, spin coating, deep coating, you name it here. It's all easy, straightforward. You can use it here. Now, so we have a huge, enormous family of materials, potentially probably the largest possible family of 2D materials. We can make these materials in large quantities, kilogram quantities in the lab, and actually I'm not aware of anyone making any other 2D material in kilo quantities in the lab here. Maybe graphene, but I also don't think solution of single layer graphene would be made in kilogram quantities in the lab here. And we can process it very easily from water, not just aqueous solution, from pure water, which is plentiful in Canada. Now, it's all great, but it is only useful if this material brings something new to its table, because if you already have clay and clay can do everything what a new material can do, why won't use clay or even graphene, which have been definitely explored to a much larger extent. So let's look at the properties. I already mentioned conductivity. So for example, you can see here a multi-layer film of titanium 332, and we get up to 20,000 Siemens per centimeter just by filtering, vacuum assisted filtration, or spreading it over the surface, or spray coating here. For people who are familiar with graphene, if you take, for example, film of reducing graphene oxide, which will look very similar way, the maximum value will get 2,000 to 4,000 Siemens per centimeter. So we get already like an order of magnitude higher electronic conductivity. And of course, it depends on the composition. Some other MXene will be less conducting. It can be up to 3-4 orders of magnitude difference. For example, niobium 2C will be just in single digits on tens of Siemens per centimeter here. But you have all this range. Now, as we already discussed, they are hydrophilic. Oxide, hydroxide, like polar surfaces, allow you this dispersion in water. And just combination of these two properties by themselves is truly unique in the materials world. But they're also strong and stiff. I'm not going to show you slides, but they're actually stronger than any other solution process to the material. If you take a single flake of graphene separated from ideal perfect crystal or boron nitride, they will have a higher modulus in strength. But every other material, including reducing graphene oxide, will be weaker. And this allows something that is a direct sequence of this, but not obvious. We can make in solution processing flakes go into, say, 20 microns and larger. You can look at all the literature, all the thousands of studies, for example, moly disulfide or other materials produced in solution, except graphene. And you will never see flakes larger than, say, a micron in size, because just vibrations in a fluid break them apart. And this strength, indirect consequence of this, leads to possibility to grow larger flakes for device application, for other things. But otherwise, they look like other 2D material. This is an optical image on a SiO2 layer, silicon wafer with SiO2 layer. But if you look in TM, you will see single layer flakes. You see this one is hanging in a hole of a grid. Again, something graphene won't be able to do. And there are single crystals. You can see it from high resolution TM and selective material diffraction. But there are many other properties. Plasmonic colors, very efficient light to heat conversion, electrochemically active surfaces, chemically, electrochemically tunable work function, and other properties. But the key thing with these materials here, as I mentioned in the beginning, you can tune their properties. You can shift the Fermi level. You can do reversible redox reactions on the surfaces here. Because nanotechnology, nanomaterials, is not about making things small. It's about controlling at the nanoscale. And this is exactly what materials allow to do. There are also many other interesting properties predicted, which again, I'm not going to discuss today. Some of them have been demonstrated, some of them not. By basically pulling electron density away from transition metal by, say, oxygen termination or chalcogen, you can open band gap making semiconducting MXenes. Topological insulators have been predicted, many of them in this family. Two-dimensional ferromagnetic, antiferromagnetic materials again have been predicted. Superconductors have been predicted actually 2 years ago. Dmitry Talapin's group from University of Chicago demonstrated semiconducting sulfur and selenium terminated MXenes in here. Many other like topological insulator, 2D ferromagnets are still to be experimentally demonstrated. Things here. So again, plenty of room to discover. So to summarize this part, what do we have? We have this very large family of materials, scalable production things, where we can control properties by changing, adding surface termination, changing surface termination, by selecting the number of layers, kind of transition metal, carbon, nitrogen, or mix of thereof, mixing different elements, M elements or X elements, making solid solution. But you can also intercalate ions, molecules between the layers. You can also, of course, chemically attach various moiety to the surface, again, not killing conductivity and thickness. So there are so many modes of design. And of course, it changes the electronic structure. And you can see from a couple of these density of states pictures in the top here. You change different elements and you see have different colors. And you have complementing plasmonic color. For example, titanium 2C will be like a red, purple in solution and green in reflection. And this is a classical case of gold nanoparticles. With the only difference, you have very common elements, titanium and carbon here, no gold. And this is the same color that Lycurgus cup, for example, from 4th century, this classic example of nanotechnology gives you, which is green in reflection and red in transmission because it contains gold and silver nanoparticles. And it's often cited in nanotechnology books, popular literature, as a first example of human-made nano systems here. And you look at effect of surface termination now. If you have OH, you get a work function of about 2. You heat it up, break hydroxyl groups to oxygen, and work function goes to 6. So for optoelectronic applications, solar cells, others, you can see how in ETL, for example, you can tune the work function to match it to work function of, say, semiconductor you use next to it, things here. So tunability is important. And of course, it can also be controlled by synthesis. You can see, for example, transverse plasmons, surface transfer plasmons of titanium-2, titanium-3C2 are different. That's why they have these different colors. But depending on how you synthesize this, what is the surface termination, it also shifts chemically. It also, properties can also be controlled by introducing defects like vacancies on the surface. They're good for some application like catalyst. We can, for example, embed also single platinum or other atoms doing single atom catalyst in these holes. For some other applications, they're not necessarily good. They may decrease environmental stability of these materials. So you need to control this thing here. And for example, like for a while, MXenes have also been plagued by moderate environmental stability. Some of them could be processed in solution for weeks. And when you make a film, for example, or I have like a pictures and paper sheets with my signature in MXene, just by filling fountain pen and signing it, made a few years ago, they're still conducting in black. But in solution, they would be able to hydrolyze after a while. And V2C, for example, was considered to be the least stable one, which would last just for hours in solution. You had to process it immediately after synthesis. Now we improved the synthesis that we can actually keep it for up to 4 months in solution and redisperse it here by, again, controlling surface chemistry, controlling interlayer chemistry, and basically changing its composition. And we increase the conductivity, say, from about 250 to about 1,000 Siemens per centimeter. So again, control is important, but value. What is also important? The fact that we can produce MXene in larger quantities allows us to actually access to many applications, not only electronics, sensors, optics, but also electromagnetic interference shields and antennas. We can print it, we can make catalysts, we can reach to environmental application. For example, again, not only sensor, but membranes for water desalination, for gas separation here. And energy storage, battery supercapacitor, what large part of my group is working on here. We have not reached really volumes required for construction, like graphene is slowly getting into concrete and plastics for construction applications, at least a multi-layer shared graphite, which Canada is one of main producers, things here. But clearly, since we deal with lot of abundant elements like titanium, titanium 2C, titanium 3CN, titanium 3C2, titanium 4 and 3. Just in that system, you can create a variety of materials. But moly, vanadium, niobium, other are quite common. They are pretty much present in almost every like a metal steel alloy that is used for a variety of applications. We can do things. And we can really manufacture it here because you see, this is like a 1 meter long, 10 centimeter wide film of MXene. It has just 1 micron thickness and you can handle it. You can basically lift it, you can handle it separately. It has strengths exceeding strengths of aluminum foil that you use to wrap up your breakfast. And 15,000 Siemens per centimeter. It was made by just taking this colloidal solution of MXene, doctor blading it over the surface and drying. Very simple, very efficient process here. And we can use it, for example, as a current collector in a battery with 10 times smaller thickness compared to, say, copper, and it means much lighter. Now, I don't have much time, and I'm going just to give you some flavor of possible application. Because what I want you to understand is there is this variety of materials with attractive properties. If you know properties of materials, you basically can look through the prism of your interest, your expertise, and think, okay, where can I use those materials? So I'm not going to focus on application, but just give you an idea of what is possible. For example, like MXene interacts strongly with electromagnetic waves in the all range from UV to radio waves. So naturally, as you can see, application going from transparent conductor to electromagnetic shielding to light to heat conversion, photothermal therapy, for example, medicine will be a good example of this, to surface enhanced Raman spectroscopy using plasmonic properties, to photoluminescence and quantum dots, to antennas and RFID text here, because we can cover all the range from UV to visible, IR, terahertz, and so on here. And for example, like we collaborated with Korean colleagues to use titanium 3C2 MXene transparent film to replace ITO in organic LEDs. And you can see that pretty much about the same properties, but with MXene, you can first put it from aqueous solution on the surface. Second, you can twist, bend, and even fold the device, and the film remains conductive. ITO cracks and degrades, so if you make it flexible, you can replace it too. Here, people showed that for all the printable devices, so on, you can replace gold and other metals with, again, MXene printed patterns here. You can put them into gel and make conducting hydrogels or aerogels, sensor and actuators, again, optically actuated because of this photothermal effect, or electrically activated here, variety of sensors, others here. To such an extent that Hussam Al-Sharif from KAUST, who is quite active in MXene research, actually in KAUST, there are 17 different research groups, as I learned from a recent article, working in MXene now. He suggested the entire area of electronics appeared, which he called MXtronics. Basically electronics and optoelectronics based on MXene because of such a variety of materials, properties, and application allow really to build entire devices using MXene or enable them in combination. Also, just take a step back. When I compare MXene to graphene or other materials, it's not like I'm trying to tell you, look, Forget about graphene, or forget about disulfide or carbon nanotubes. The idea is here, we need a variety of building blocks. Whatever you build, you cannot have bolts and nuts of one size and tell, look, we're going to build everything. Exactly really the advantage is that when we have this variety of materials, we can select from those which one is right for right application. In many cases, we also build hybrids. For example, we hybridize and combine MXene titanium 332 with moly disulfide, or with graphene oxide, or graphene, depending on application we use, or with carbon nanotubes to improve accessibility to the layers in electrolyte and battery electrodes, these things here. So again, it is important, but again, it shows how quickly the field grows here. Let me also give you a couple of examples where, for example, MXene entered the field and really changed it here. One is electromagnetic interference shielding. So pretty much every device here, microphone and this camera, a cell phone here, needs shielding, because otherwise all these devices will interfere and you won't hear me. And sometimes this awful sound when someone comes with a microphone close to dynamics or close to another mic here in the room. So traditionally, metal is used, and you can see the thick metal grid sometimes in the microphones, professional mics that are used here. MXenes, in this paper, we published first paper in 2016. Aligns with actually much more conducting copper or gold and aluminum, but allows us, remember, make 1 to 2 micron films, which gives you like a 50 decibel shielding. And 50 decibel, it basically means 99.999% of signal reflection. But metal, you cannot make 1 micron freestanding film. You take 10, 15 micron usually foils, and MXene, you can take it with 1. So it was a really very big breakthrough in the field. And in 2019, in this next paper, 2020, sorry, we showed that carbon nitride MXene, which is less conducting than titanium 332, outperforms at the same thickness, even much more conducting metal like copper. So it really opens opportunity to look into really what are the interaction between electromagnetic waves, which have centimeter wavelengths, like in the X band shown here, and 2D material, which no one really studied carefully before. And the effect of this discovery on the field was such that this 2016 paper in Science, within 5 years, became the most cited ever paper in the entire electromagnetic interference shielding field, which is, of course, very, very old and established field where a variety of carbon materials, graphene, nanotubes have been explored since here. You see how disruptive can be arrival of new materials to the field. And this technology has already been licensed to a major Japanese electronic company and then used. And of course, you can use different materials. You'll have different properties with different shielding. Some of them will be more absorbing, some of them will be more reflecting. You can design this here. On the opposite side of this things here, instead of shielding, you can use it to basically transmit the signal, produce the signal. You can use it as antenna. And recall again, we can print them, we can make them into fiber, textiles, we can put them on any surface, we can make them very thin. So we can produce antennas for wireless communication, for example, for 5G antennas. And again, we can print them by inkjet printing. You can see it also in this paper from John Jung that I mentioned today in Nature Communications. This was published again about 2 years ago by our group. Things here, depending on shape, size, you will get different frequencies for these antennas here. But what is important? They give you up to 99% of radiation efficiency of copper antennas, being like a 10 times thinner and lighter, and again, printable on any surface, flexible, bendable, and so on. You can use them also as a sensor because as you bend the antenna, it changes the frequency or stretch it if you have a, for example, textile antenna things here. So you can go this way. In my group, we work a lot on electrochemical application of MXenes. And again, why I believe personally, they can make a big difference here. Because in this plot, and if you have seen lectures by Linda Nazar, you have probably seen something like that here. Everyone is trying to get to area of high energy and high power. When one stores as much energy as current batteries, but can charge these batteries within, say, minutes, not hours. And do it without killing the battery, doing it hundreds, thousands, millions of times here. So what people try to do is to combine principal electrochemical capacitor, surface storage, with batteries, redox storage. So you need materials which can, first, no solid state diffusion, because solid state diffusion will always kill at the power at the rate. You need material where redox is on the surface, but you need to have redox, because double layer capacitance of carbon will never give you physical storage, will never give you the same amount of energy as you get from electron transfer redox reactions. But what is also people forget very often, what does it mean fast charging? It simply means running high current through the device. What happens if you have a poorly conducting material like a ceramics using batteries here and try to run high current through a poor conductor? You get Joule heats, right? Everyone knows it from high school physics here. So we need materials which are electronically highly conductive. And MXene potentially offer this both. They offer electronic conductivity, which is orders of magnitude higher. For example, activated carbon using supercapacitor, which are our fastest energy storage devices, has about typically 100 to 300 Siemens per centimeter conductivity. We can go 2 orders of magnitude better with MXene. Transition metal on the surface gives you opportunity for redox. There are galleries between the layers that can transport ions, things here. So pretty much we have everything we need to create materials that can store much energy and do it quickly. And moreover, there are no phase transformation into the material, so it can be a long lifetime here. Not surprisingly, many of the things are already been done. And actually, Professor Linda Nazar was the first one to publish on lithium sulfur battery applications of MXenes. And also one thing I forgot to mention, I referred many times here. You can also see name of Bach Anasuri here. And some of you, he was one of the key contributors in developing and discovery of this out of plane ordered sandwich-like MXene structures and exploring a number of their applications. He is now a Wien Fellow, rising star here, so I'm sure you'll be able to communicate with him here. But basically, people have been exploring almost every kind of possible battery supercapacitor applications here. And we showed that, in fact, what we have been claiming, very fast redox is possible. If you look at this cyclical tomogram of MXene in protocol electrolyte sulfuric acid, you will see that close to OCP, there is like a double layer storage, but there is this wide redox peak overlaid on it. And actually, the separation is about 20 millivolts. So we call it in electrochemical reversible reduction. So it's basically a symmetric peak. But moreover, this peak, while it shifts, but it stays up to rate of 100,000 millivolts per second, 100 volts per second. So for 1 volt, it's 10 millisecond charge. So it means that, in fact, in batteries, we're not limited by redox reaction rate. We're really limited by transport of either ions or electrons. And if we have highly electronically conducting material, we really need to design the architecture, because as layer gets thicker, ions move slower. There's a long pathway here. But it shows fundamentally that it's possible to create devices I'm talking about. Moreover, there are a lot of things, of course, a lot of challenges. For example, depending on type of even solvent we use in ions, we can get situations where we get ions co-intercalating with the solvent, or we can get complete desalvation and go just pure lithium ions into the layers. So again, with 2D materials, we can go all the way from double layer capacitors to batteries simply by controlling desalvation of ions that intercalate between the layers. And we just published, like very recently, this perspective article in Nature Energy describing it. So again, you can do engineering, not just by taking some discrete materials, by simply, like again, controlling at the nanoscale materials and electrolyte use. And of course, when you work with 2D materials or low dimensional materials, same will be true for 1D nanowires and nanotubes. You need to use advantages of those initially, because before we come to like a cars and truck batteries and produce really millions of tons of materials here, we can take advantage of them where you cannot simply use conventional materials in flexible devices, in wearable, kneadable structures, printed electronics, microchips, when you can, again, it's probably very difficult to distinguish, but there are 100 interdigitated microsupercapacitor. Here we can again do, for example, operation at very high frequencies. Like basically you can do a CDC conversion with those, but they are on a chip much smaller than electrolytic capacitor things here. And you can again even like a neat devices here. Also, what is important, I stressed it several times, you can make like a thinner films compared to metals. You can use it as a current collector, but much thinner, much lighter compared to metal. Moreover, MXenes, for example, are stable in halogen-containing environment. So you can use, for example, chloride electrolytes that cannot be used with metals. It's a major pain for these applications here, or water desalination, electrochemical. And they also suppress dendrite growth. So lithium grows or sodium parallel to the surface, which is again a very big deal in developing sodium sulfide, sulfur metal, lithium sulfur batteries, and in general, metal battery things here. They can be used as conducting binder. So you can use a current collector, use conducting binder for cathode, anode materials, carbon, silicon anodes, and other applications. Again, I mentioned suppressing dendrite growth, making stable growth here, adsorption of polysulfides, catalytic decomposition of polysulfides, and again, making conducting cathodes. Linda has priority in the field. Or you can actually combine different properties, and you can make electrochromic plasmonic device, where you can have a shift of, like in this case, TM32, just with 1 volt, 170 nanometers. So you can go basically from green to blue with 1 volt applied. But moreover, it's not conventional electrochromic device when you change the state. It's actually you shift a plasmon resonance, surface transfer plasmon peak, which only depends on the thickness and the electronic properties of material. You change it here. So again, gold nanoparticles, if you take, it will just stay gold. It has 550 plasmon, it will 0. You can change the shape and you can change the plasmon, but you cannot control it. Here you can tune this plasmon, which again opens new avenues in plasmonics. And there are many other applications people are exploring nowadays, which I just didn't have time to talk about here, because beyond energy storage or optoelectronics, again, very important potential environment applications, separating hydrogen, for example, from methane, or water desalination, deionization, filtration, purification, like, and again, by applying potential, you can do things that other materials cannot do because say with polymer or with oxide clay filters, you can do filtration, but you cannot control it electrochemically. With graphene oxide, you can do the same. Very nice membrane was shown by Manchester Group, for example. But when you make a graphene, it's hydrophobic. MXene is hydrophilic and electrically conducting. So you can again run current through apply potential and control rejection, for example, of certain ions or molecules here. Electrochemical sensing, optical sensing, strain sensing, another very big field. You can do acoustics, you can do resonators, you can do speakers. We had a senior design team which won patented technology, won a prize in our Drexel senior design competition 2 years ago for designing MXene speakers, things here. There are many biomedical applications. We work on application ranging from urea adsorption for making wearable kidney, and actually technology has been transferred and a startup company was created in the US to explore it here, to conducting epidermal and implantable electrodes, to photothermal therapy for cancer treatment, as I mentioned here, and many, many others. Again, you know, like my approach is always in our group here. We work from discovery to application, but we do it in a fundamental way. We discover, synthesize, modify material, learn how to control them, measure property. And then we think how to use them, in what application they can be useful. And I encourage you to do the same. look at the properties of MXenes, think of available composition structures, type of materials, and think where you can apply, where you can use it here. And if you don't have available MXene, as I mentioned here, only about 50 of the infinite number have been produced, so you can make your own MXene with properties needed here. And what is nice, of course, already it's moving to the stage where industry comes in. There are more and more companies working on it. There is an association, MXene Association, that you can also join here. And actually, this is almost the last slide I'm going to show now. This is my research group, actually picture taken a year ago, one of the first post-COVID gathering in my backyard when we celebrated summer and successes of the group. Those are these students, postdocs coming from at least a dozen of different countries who really do the research I showed to you. That's all possible because of their wonderful efforts here. But even that is not enough. We collaborate with people virtually all around the world, at least from, at the moment, 20 different research groups from Australia and Asia to Europe and of course US, because we're tackling so many different problems, areas where I have no expertise, no prerequisite knowledge or equipment to do the studies, from killing cancer to building antennas and microelectronic devices. So we would not be able to do it again. Collaboration is the key for tackling interdisciplinary problems. But this is where progress can be done. This is where breakthroughs happen. Because people who traditionally design antennas or EMI shielding were not aware of MXenes. And of course, being a material chemist, I knew nothing 6 years ago about electromagnetic interference shielding. And by combining properties with experts in the field, we really made a revolution in the field very quickly. So again, I encourage you to talk to people outside your field. Go to seminars outside your direct field, and having an institute like you have WIN is a great opportunity because it brings together people working in so many different disciplines and utilizing nanotechnology, nanomaterials approach. And my very last slide, there are already multiple conferences dealing with MXenes, specifically like at the MRS meeting, Material Society meeting in Honolulu 2 weeks ago. There was a symposium on MXene. There will be another one at the fall MRS meeting in Boston in late November, early December. There will be 4th international conference on MXenes in China, in Nanjing, in August. And also we have our second MXene conference. The first one in 2020 actually went completely online because of the pandemic. This time we are planning to have it in a hybrid format. We have lots of speakers already coming to the conference, and it's not too late to submit an abstract till the 17th. So this next week, we're accepting still abstract, and join the conference. We have very nominal fees for attendance. And this is an opportunity to learn more about materials. Moreover, if you can come to Philadelphia a day before, we will be on the, actually before August, on the 31st of July, we will give you 1-day course in conjunction with this conference, and we teach people how to make, characterize MXenes. And this is an opportunity to learn. And also, I know that there is significant support from your university to Ukrainian scientists. I've read that University of Waterloo invited a large number of Ukrainian students to work here. And we also offer, of course, free registration and should be able to provide financial support also for travel to Ukrainian scientists here. And this is my very last slide. Thank you very much for your attention. I will be glad to answer questions.
So what we'll do is we'll try to fill some questions from here as well as from the online audience. Already some questions are coming in. So perhaps maybe we'll start a question from here. From the audience. Yes, please.
This was very interesting and very inspiring.
Thank you.
We feel really lucky to have you here in person, to finally see a person whose books and whose papers we have been reading as a reference course material. So, first of all, thank you so much for being here.
You're most welcome. Thank you for invitation. You know, you should thank your center director.
Talking about the MXenes, like we have been having that since 2011, and I always thought about like with each discovery of these sort of new materials, let it be the MXenes or be the perovskite, each decade or so we get to hear about some new sort of materials, and we hear about that how they might be able to replicate some properties of the existing materials, or maybe even be able to potentially replace them in coming years. But your talk maybe focused about the pros of the MXenes, right? So since you have been working over a decade on these materials, have you faced some sort of issues related to the instability of these materials, or some sort of hindrances that might actually be like stopping the commercial viability of these materials?
That's a good, a very important question. No material is perfect, not even MXenes. As with any other material, there are challenges, several challenges. One is, as you have heard from my presentation, we need max phase or another layered carbide nitride precursor. So this makes the process complicated. And actually, currently, probably about 90% of cost of manufacturing is the cost of these ceramic precursors. So if we learn how to make them by directly, say, transforming graphene into molybdenum-2C, it may become much less expensive. So synthesis, cost of synthesis. Initially, we used HF. It's a good for industry. Industry tells us chemical industry is cheap, but for example, even for research, it's many laboratories have restrictions. It's a dangerous chemical to deal with. So minimizing synthesis here. I have not included it here. And oops, let me go back as I'm talking to you to a slide here. But in our perspective in ACS Nano in 2020, we published a list of 30 big open questions in MXene field that need to be addressed, formulated by scientists working in the field. And I'm trying to find one already jump here, which there was an ACS Nano. Okay, in this April 2021, sorry, it was a year ago published article here. You will find a list of 30 problems and questions, and participants of the third international conference MXene voted for them to basically set it up. Number one was safe and scalable synthesis of MXene. We greatly improved scalability over the past year. We minimized like a decreased amount of water used from like 150 liter to about 5 liter for 100 grams. Oh, sorry, for kilogram MXene and so on. But still issues remain in max phases. We're looking, for example, for SHS synthesis. Another big issue was, I mentioned very briefly, stability. MXenes can hydrolyze. It's carbides, nitrides. They can react with water. They can react with oxygen. It appeared that stoichiometry, transition metal carbon stoichiometry, is really the key. Point defect on the surface, overreaching is another question here, and flake size. So if you control them, we can now make titanium 332 MXene, most common, most widely used, about like a 20%, 1/3 of all publication MXene are on titanium 332. Stable as single flake at room temperature in dilute solution for at least a year. As long as it's a closed vial in a dark place, it will stay for a year. So again, many problems are solvable, but you need to address them. You need to do the same. I showed you for V2C because this was example of like a archetypical unstable MXene. And it's possible to push it at least for a few months in solution. Things here. So those are some of the limitations. And again, some properties that are good for one application, say polar surfaces of MXene, good for mixing with polar polymers. You can bond them chemically to epoxy. But if you want to mix them with polyethylene or polypropylene, they will not love them right here because there is no interaction here. So I think that's why here. And I really suggest you to look at this article. It has a list of the 30 questions. Actually, it's a great starting point for some of you who want to tackle unsolved problems in the field. You can just have them formulated and you know, okay, this is a target here. Of course, it needs to be updated now a year later, but most of questions, majority of them still need. Other thing, and I know this is a very long question, but those are really important points. I was again telling you that's a great when used chemical method for synthesis. It's kind of analog of graphene oxide and solution process in graphene, something a la Rodruev, but not Andrei Gaim, Kostin Novoselov, CVD, PVD synthesis. For a number of electronic applications, people would love to be able to produce monolayer MXenes in your clean room by vapor deposition techniques. And people make ultra thin, like a few layers, couple of nanometer films, but there is no good controllable way to make wafer size MXenes. But if you go back a decade or so, also very recently, no one was able to produce wafer size graphene or molybdensulfide or boron nitride film. You just need to put effort into this and it becomes possible. So yes, there are many problems to solve, like with any new family of materials, and those are the one you should pick, not just built on like electrochemical supercapacitors that have been developed for 10 years. Pick problems that have not been solved. Pick applications where people have not used MXene yet, but it can not only like do as good as another material, but when it can make a real big difference here. And then you will have a new important science done.
Yeah. Let's pick a question from the online audience.
I can also read them out loud.
Yeah, why don't you read it out?
Yeah.
How exactly were MXenes discovered in the lab? Was it an accident or deliberate and consistent work? Were they predicted to exist in advance as graphene was?
They were not predicted to exist in advance. No one really expected that. And this is a combination of basically, to a certain extent, discovery itself may be accidental. To keep a long story short, I had an idea that titanium silicon carbide, titanium aluminum carbide max phases can be good for anodes of lithium-ion batteries. It was the time people started to work on silicon anodes. And I thought, okay, look at this layer of ceramic, titanium silicon carbide, which I just had here. It has layer of silicon, which can take more lithium than carbon. It has metallically conducting layer of carbide, which will provide electronic conductivity. Potentially great anode materials if lithium get inserted. One of my students, Murat Kurtoglu, did DFT calculation and showed that the barrier for intercalation is not very high. So we wrote a proposal to DOE. I invited Professor Michel Barzoum, who was working on max phases at Drexel, to join. And we got $1 million for developing max phase anodes. Unfortunately, lithium did not know about our DFT calculations and totally refused to go into the structure. Years later, we showed that making nanoparticles and so on, we can achieve it. So what we decided to do, to use an approach that I've been using for a long time, the selective etching, to like open channels for lithium to go in and etch it here. And Michael Naguib, student who was working on this project, he's a professor in Tulane now, Tulane University, by the way. He tried titanium silicon carbide and again failed. My other student, 6 years later, etched titanium silicon carbide to make them silicon. But he tried a number of other materials. He tried a number of different etching. And finally, by using HF solution, he made titanium 3C2. And initially, when my other postdoc looked at TM, he told, oh, you made graphene because there are two-dimensional layers instead of under etching. But when we looked, we realized that closely did EDS and yields, we realized that this is not graphene, this is two-dimensional titanium carbide. And the rest is the history. After that, we realized we can make many other materials and so on. And the process started developing here. So it is serendipity. It's a luck, but you know, you always need to think be inventive and think, okay, if you have an obstacle, what is the way to overcome? You can find something new. I think there was another question from the audience.
Yeah.
Sure, thank you. Impressive. I just focused on the application you have done in your group. So which one you think is more promising?
Look, at the moment, I would say clearly electromagnetic shielding is there. It can do things that no other material can do today. So I think this is like a low-hanging fruit. This is the first one. I'm very much excited about this urea adsorption. And again, this is something predicted by my colleagues that, small molecules can be strongly attracted here because it can really improve quality of life and even save life to millions of people who have to go a couple of times a week to dialysis and sit for a few hours at the dialysis machines. I am very much excited about optical optoelectronic plasmonic application, if I know little about it here. And of course, since I know somewhat about electrochemistry from almost 20 years of experience with supercapacitor, we work a lot on electrochemical applications. But I understand that application requiring small amount of material, really for most of shielding applications, we need a film which is just like 100 nanometers. And we can cover huge number of electronic devices. We can cover a stadium with a shielding field from a batch we can produce even at the lab. So this will be like a first application. But if you want to build batteries, for example, real size batteries for even like a computers, we need to start producing much larger amount of materials. And competition is much larger. So I think this is something again you need to consider. Something maybe low-hanging fruit, something maybe very important, impactful if you solve the problem. Something like if you get the best material for lithium-ion battery, making the industry change to MXene, I don't know what it will take. It's almost impossible just because there are all these plants working and using certain technologies things here. So those are again considerations here. Some application you can solve the engineering problem, but it doesn't mean that it will become economically viable, justifiable for industry. And this is something I think worth of thinking here. But if you want to make batteries that will store more energy, like lithium sulfur, sodium sulfur, and enable some flights in outer space where you just need to get more. If you want to make flexible, wearable batteries, this is a thing where again, there is a chance, and this is something we are trying to explore.
I think with those killer applications, I think we have to end this interactive session. I know there's a lot of questions you have, but I think we are so fortunate again, Yury, that you are here with us.
Look, it's truly my pleasure. I just moved to the first slide because there is my email here in our website.
Yes.
And you can find a lot of information about MXene if you go to my group's website. There are also our papers in PDF format, and password is NMG, like Nanomaterials Group here. And again, if you have further questions, feel free to email me and I will be glad to answer them in person. Again, thank you very much for your attention.
We will have a plaque for you, which we'll send it to you at your home, as well as we'll put it in our Hall of Fame. That you
Thank you very much. Truly appreciate it.
Thank you. Thank you, everyone.